So let's see a little bit in better details how aerodynamic lift is created. So how this aerodynamic flight principle, which is, as we have seen, the most efficient way to fly, does actually work. And the science concerned with studying this is called aerodynamics. So it is the branch of fluid dynamics concerned with studying the motion of air with a certain velocity, with a certain speed, particularly when it interacts with a solid object, like for example an airplane wing, right? And this interaction is basically what creates the lifts, and we're going to see how this how this happens. So understanding the motion of air around an object is often called enables the calculation of forces and motions acting on that object based on the flow field, right? So this is called the flow field, and this flow field includes a certain values of specific flow field variables, what we call variables. So this is specific numbers, like we're going to see which numbers are here we're concerned with in order to understand the lift. So that includes, for example, the pressure, the velocity. There are some other flow field variables as well, like the temperature, the viscosity of the air, the density of the air, and so on. So it's quite a little bit complex physics of the gas itself. And the aerodynamic forces and moments on the body are due to only basic two sources. So this is the pressure distribution over the body surface, so the main flow field variable that we're concerned with in order to understand how the aerodynamic flight principle is created. So we are concerned with the pressure distribution. We're going to see how it works, and also the shear stress distribution, which is a little bit more complex. We're going to see this in the aerodynamics course. So if you'll have a discipline by itself, the aerodynamics, are going to see all of the details about these flow field variables. So now we're just having an introduction. So we'll only touch the basics of and the tip of the iceberg, while other things and all the details we're probably going to come back to this point later on our course. So flow field variables include, again, the pressure, the density, the velocity, the temperature, as well as the viscosity and the thermal conductivity, as written here below in this slide. So let's start with the pressure. So it is the absolute value of normal force per unit area exerted on a surface due to the gas molecules impacting and or crossing that surface. So if we have, for example, a gas, the basic definition of a gas as opposed, for example, to a solid or to a liquid is that the gas particles are not connected to each other. So every particle is tumbling around, not having to do with other particles. And by having a very low interaction between the particles themselves, that means that the particles interact with any surface or any object we place inside of that gas. So no matter how big the volume the gas is placed inside, if we place any surface in any direction, the particles of the gas are going to cross this surface at a certain manner, certain frequency, and at certain intensity, depending on the temperature of the gas, in fact. So temperature is a measure of how fast things are moving, and the higher the temperature, usually the higher the pressure. It means that any surface is experiencing a pressure by the gas. So the gas pushes against any kind of surface and any kind of objects that is placed inside of that gas, right? So it is a basic flow field variable that says quite a lot of things about the flight principles. We're going to see how it works. So in terms of how this is calculated, for example, well, just the notion itself, right? So in order to understand it, so it's a force on, for example, a certain spot, which can be very small, like for example dA, which is a very small area. So when this area goes to zero, so the limits of this ratio, the force divided by the area, when the area is very small, it gives us a point value of the pressure. So we don't have to have a certain specific, for example, 1 meter square surface or 1 millimeter square or 1 centimeter square. So it can be a points value, and that's a very important thing. In fact, we can see how. So in every point in space, we can define the value of the pressure. And in fact, when we say a point, that means that it doesn't matter in which direction we are looking. So for example, if we say a certain point in space, so the pressure is acting in every direction, right? So it's acting on this direction, on the opposite direction, and in all possible directions, right? So that's why we have to shrink that area needed to define the pressure to be a point, right? To be a very small point. Okay, let's see how it works in the real life, and all, for example, the pressure distribution around a solid object, for example. In this case, this is an airfoil, or this is the cross-section of a wing, right? So an aircraft wing, if we take a cross-section, this is basically what it's going to look like. And if this wing is immersed in a moving object, in a moving air or some other gas, for example, indeed. So as we said with aerodynamics, so let it be air, right? So because the air is moving at certain velocity, at certain speed, when it interacts with this solid object, which is the wing airfoil or the wing cross section, as you can see here, we have a certain distribution of the pressure, or we have what we call a pressure field, right? So we have a field means that values which are different in each points of around this object, right? And the red color here indicates a very high pressure, while the blue color indicates a very low pressure or depressurization, right? While high pressure means pushing against the object, while low pressure means like a sucking force, means that it's like a vacuum cleaner, a force that is acting on the opposite direction rather than against the surface. Here, right? So here, the basic thing that we can notice from this pressure distribution around this airfoil is that there is a very large red spot just before the airfoil, right? So it is the force that is preventing the airfoil moving forward, right? So the airfoil is moving forward, given that there is an engine that is pushing the aircraft forward, while this red spot, which is just at the nose of the airfoil, the leading edge of the airfoil, it is a force that is dragging it backward, right? So it is preventing its motion forward, so it is drag. So the red spot, the large red spot is drag, while as you can see, there is a very large blue region just above the airfoil, right? And that's actually where the lift comes from. Now it's quite difficult to understand why there is a low pressure there. It has to do with the fact acceleration of the flow, which and then there is the Bernoulli law. We're going to study this in the course of aerodynamics. We're not going to get a lot in to the details, but the main point here is that we have a difference in pressure. There's a very low pressure above the wing, and there is a high pressure beneath the wing, and you can see it a little bit here in the trailer net. There is some yellow, red little spots here beneath the wing, and this difference in pressure means that there is a force, right, that is experienced by the airfoil because of the difference in pressure. And this is, in fact, what generates the lift. And surprisingly enough, thin air, which we can say, right? So it is very thin. So it has very low density. But because of this difference in pressure, it can be so large that it can take. So it can overcome the gravity even for a very large aircraft, for example, like 100-ton or 200 tons airplane or airliner or cargo plane or military airplane. And it can overcome all that gravity just because of this difference in pressure. So this low pressure above the wing is in fact a very large force. It can be as much as 100 tons, for instance, right? Depending, of course, on the flight speed and the size of the wings and some other factors. And now this is rather a bigger picture of the flow field around the entire airliner. And here also you can notice that there is a very large blue region just above the wing, which also means a suction force, a low pressure, and that's in fact the source of the lift. And some red regions here. You can see also the origins of the drag, which also prevents the aircraft from moving forward. And there are some other sources that we're going also to see today. And you can see this condensation over an airliner wing due to low pressure on its upper surface. So if this is just to see if the computer graphics, if you like, so this is the real lift and how it is generated. So you can see the cloud over the wing. So that's just how much low pressure. So you can see it doesn't have to be on the surface of the wing itself. So it's a very large cloud just above the entire aircraft, right? And condensation happens here because of low pressure, with some cool temperatures and some humidity. So that's why you don't see it all the time when the aircraft is flying. So if you, for example, check and don't see the condensation, that doesn't mean that the lift is not being generated. It just means that it's not the right conditions for condensation to happen. But when it happens, it allows us to visualize the flow field, right? It allows us to see the pressure, the low pressure above the wing. And in this beautiful picture, it is demonstrated just how much lift is being generated above this 777, I suppose, aircraft. So it's a very large aircraft, so it weighs about 250 tons, for example. And you can see that this low pressure, this sucking force above the wing is large enough to keep the aircraft airborne, which is quite amazing for taking into account that origin is only thin air, right? Now we can move on to, so again, the details of how this happens and how it works are going to be studied in much better details in the aerodynamics course, and probably if we're going to have a dedicated lecture only for aerodynamics, I'm going to come back to these points and see some other beautiful details also for how this process takes place and so on. But for now, we can move on to see some other classification criterions for classifying different aircraft according to their mission profile, right? And the mission profile basically divides every aircraft into two big categories: the civil aircraft and the military aircraft. And basically, the design tasks of these two big categories is different in terms that the military aircraft is usually having especially for example, fighters, we're going to see the classification here, for example, a little bit later. Here, the basic point is extending the frontiers of flight, if you like. So it's extending the flight envelope, right? Making the aircraft fly faster, higher, and more, for example, more maneuverable and so on. While the civil airplanes, their main mission profile or their main task is to have the best economy, right? The best fuel economy. So that's basically the difference in the design philosophy of these two big categories. And they themselves, civil airplanes, as you can see here, they can have, depending on the mission profile, passenger airplane, cargo airplane, special purpose airplane, trains, you name it. So it's quite different. So the aircraft can perform pretty much any task that has to do with air transport and some other tasks, including the rescue, firefighting, air tourism, agricultural, and so on and so on. Right, and depending on basically two things: the flight speed and the flight altitude, and also the flight range. Right, the range, the distance that the aircraft can cover. We can also classify passenger airlines into intercontinental jets with over 11,000 kilometers of range. Some medium-range airplanes which can fly a little bit closer than that. For example, 5,000 kilometers, like for example the most common airplanes of this category, like the 737 or Airbus A320, that can fly approximately 5,500 kilometers of range, or a little bit more than that, depending on the configuration of the aircraft. And finally, there's some regional airplanes that can fly only less than 5,000 kilometers, for example, all smaller jets that can cover about 2,000, 3,000 kilometers, so just quite regional aircrafts. And as you can see, the medium range itself can be divided into the long haul, medium haul, short haul, and finally, we have the cargo airplanes, special purpose, and the trainers, initial training, transitive trainers, and so on. So, in fact, of course, this diagram doesn't include every aircraft that flies in the world. There are some other categories as well, the research aircraft, which are dedicated to study the physics of flow, for example, certain high altitude aircraft, or, for example, I don't know, some other types of missions that are not included here. So this is just a general picture of the classification. And here's some intercontinental jets, for example, 747, some medium-range airliner, and some regional jets, right? So you can see, depending on the size of the aircraft, the range is a result, right? So for example, intercontinental jets, big aircraft, is designed to take quite a lot of loads of fuel and payload, and it can cover pretty much unlimited distances, or of course, just pretty much unlimited, so it's like 20,000 kilometers, so it's a very large distance, while these guys can cover only some little distances up to 5,000 and even up to 9,000 kilometers, so that's considered a medium range or a regional aircraft. Some cargo aircraft, you can see the peculiarity here. The difference is that the wind is a high wind, so that eases up the access to the payload and loading the aircraft, unloading the aircraft, and so on. So you can see how the mission profile also shapes the aircraft itself in terms of having the possibility, for example, to load and unload the cargo, for example, passengers, and so on and so on. And some special purpose aircraft like recreational general aviation aircrafts, which is the lightest type of this aircraft, the slowest, and it flies very small altitudes. Some research aircraft, high altitude aircrafts, which flies at very high altitudes in order to gather some data that is required at high altitude. For example, studying radiation at those altitudes, or studying the weather forecast, and so on. And some firefighting aircraft, which is also a very useful type of aircraft that can take off and land from water, for instance. And let's see this general also classification of military airplanes. Here we have the Air Force, the aircraft, the carrier aviation, the air defense. So the Air Force basically includes tactical aviation, strategic aviation, which is long-range bombers and so on, and some military transport aviation, which is a little bit has to do also with the cargo aircraft. So pretty much it's the same type, can be used both as military transport or as civil transport. So it doesn't matter what is the mission profile. And the aircraft, the carrier aviation, which is designed to take off and land from carriers, from ships, and the air defense aviation, which includes, for example, fighter interceptors and so on. So as you can see here, the largest part is, of course, the Air Force, which includes the largest part of it, which is the tactical aviation, the fighters and the fighter bombers and so on. So here the main design problem is extending the flight envelope, making the aircraft again fly higher, faster, and at more maneuverability, and also, in fact, today's technology implies less radar, how this is called, the cross-section, and some other flight performance that has to do exactly with performing very specific tasks of the military or the Air Force aviation. So basically, this is the classification. Now we can see this final item for today's lecture. So the aircraft life cycle of a product is a sequence of processes since the moment of initial order or the design task by a customer until the manufacturing of the product, its consecutive operation, and final removal from service. Right. So this is the entire life of the aircraft. Right. So from before its birth, if you like, and up until its death, which is removed from service, and passing through all of these distinct stages. The research and development, the finalized, initialized concept, the preliminary design, the final design, some experimental prototype, the physical, the first aircraft which is born basically in this stage, then the flight tests, the mass production, and finally operation, which takes quite a lot of years. So aircrafts are operated, for example, for a few decades, up to 40 years. For example, there are certain aircrafts like the B-52, which has been operated now for more than half a century. So it's quite a very large time scale. And finally, the removal from service, which is also a part of the life cycle, which is the final part of the life cycle. And from this pie chart, we can see that the operation, which is by far the largest in terms of time scale, it takes only half of the cost of the life cycle of the aircraft, while the mass production and the design stage, they consume quite significant, the other half, if you like, of the cost of the aircraft's life cycle. And in fact, nowadays, the design stage consumes very large amounts of time and money. And in order to, for example, design an aircraft that is has to do with, for example, a new generation or some new performance level, we can count up to 10 years in order to have an aircraft that is quite a new level of performance, or, for example, a new type of aircraft, or an aircraft that is designed in order to create a new level of competitivity and so on. So the design stage nowadays and the research development can consume even more than the mass production of the aircraft, because it takes quite a lot of work from thousands of engineers in order to have this kind of over-engineered machine created and designed. So that's basically how the life cycle, what is an aircraft, how it flies, and I suppose that's a good introduction into our course in terms of understanding what is an aircraft in the general context of the aviation complex, and by itself as a system, what is it made of, and how it starts its life, and how much the cost of its life cycle.